In the previous video, we considered a simple sort of one bus architecture with some memory, ALU, a bunch of registers, etc. And we looked at a single instruction, load the accumulator, where the operand was the address. So we took that address, put it into the NAR, and got the data at that address and loaded it into the accumulator. And so now we want to go down and sort of take those steps and really think about them as ones and zeros to sort of talk to the hardware and get this action of loading the accumulator accomplished. So we said we had all these pieces in our architecture, and all of those pieces had things they could do, like take something off the bus, which was load, put something on the bus, which was enable, and they just had to be told to do it by their sort of by that pin on the device that gets it to do its thing. And so we're going to start sending, imagine the ones and zeros of telling something to like perform its action or to just rest. Okay, so, and then these, we can imagine that those action signals are a way to communicate with the hardware and therefore can be considered at least a possible version of how to get the microcode, how to get a ROM to talk to the hardware and make it do what we want. Okay. And again, this is the microcode. So the the Load Accumulator A is considered a machine language, but we're down at a sort of lower level where that one instruction may be a number of actions of the hardware. Okay, so again, we're doing a Load Accumulator A, and we're going to assume, I'm going to make a simplification here. And so we have all these registers in our architecture, and we're going to imagine that they all have things they can do. They all have these control inputs, and we're going to imagine that they're all sort of active high. So if we wanted to do something, we send it a 1. Otherwise, we let it sit at 0. And again, here is that architecture. We have some inputs. We have some outputs. We have the program counter, the memory address register, memory data register, instruction register, which talks to control. The accumulator and the temp talk immediately to ALU, which talks to flags. We have B and C to do hold extra little things, and we have output ports. Okay. And the first step, we said that the program counter was telling us where our next instruction is. And so if we want to get our next instruction, we got to take the value that's in the program counter and put it into the memory address register. And the program counter has an enable pin that allows it to put its value on the bus. The memory address register has a load input, control input, that allows it to take its value off the bus. So that first step, we can imagine as being sending a 1 to the program counter is that the enable, and a 1 to the memory address register, or MAR's load, as 0 to everything else, and that will accomplish our first step. So now we're at the level of understanding it and as ones and zeros, 1 to do something and 0 to not. So the first step, get the value from the program counter to the memory address register, send an enable 1 to the program counter, a load to the memory address register, everybody else stay put. Our next step was to prepare for the next time around, and so to increment the program counter, and so we make that active and leave everybody else alone. Okay. So that was a pretty simple step. Now from the first step, from that address state, we were pointing at within memory, and all the things we can address in memory, we are pointing at the next instruction. We want to read that instruction and put it into the instruction register. So there are two things, two main actions in memory, read and write. And so we're imagining a read action pin and a write action pin. We have the data, we want to get the data someplace else, so we need to put it on the bus. We don't connect every part of memory to the bus. We connect the memory to the data register and then the data register to the bus. So when we said memory read, that put the value that we are pointing to into the memory data register. Now we want the memory data register to put it on the bus, so that is an enable action. And then the instruction register is going to take that value in, so it is loading. So we send ones to those. Those are the actions we want, so those we send ones to, and everything else we send zeros to. And so all the ones and zeros you're seeing right now, those are the fetch cycle. Now we are ready to execute. We're doing a load. And so we imagined in our simple architecture that some of what got into the instruction register was an address. And so we want that address off of that instruction register. We want that to come off out of the instruction register and onto the bus. So that is an enable. And then in the memory address register, again, that piece of data was an address, so we wanted the memory address register, and so that is a load. And so that was our first step of the execution cycle, were those two ones. Now we are pointing at the data we actually want in the accumulator. So again, we are reading memory. Reading memory puts it in the memory data register. We want that value to be put on the bus so it can be communicated elsewhere. So that is memory data register enable. And then we're going to take it into the accumulator. So that is accumulator load. So that is the all those ones, those are the actions of our fifth step. And just to sort of keep most of our instructions sort of a similar length, we might have a more complicated instruction like load indirect. So we're going to imagine a sixth step where we do nothing. And so that would be all zeros. And so these ones and zeros we see are the sort of, we can imagine that all of our little parts of the computer have these control pins, have different things they can do, have these control pins. We are sending them signals of whether to be active or not. Mostly you see zeros, only one or two things are at any one step are doing something. And so we can imagine these ones and zeros being the ROM, being what we burn, the instructions, the microcode that we burn into ROM to get the hardware to do our instruction. So these ones and zeros we can imagine are what I'm calling the microcode, a level down from the machine language, from which is in memory and is software. So that load accumulator A, that was one instruction in a machine code. It corresponds to a number of steps in microcode, and most people won't program at this level, but but somebody has to. So somebody does this microcoding, this microprogramming. And while you probably haven't programmed at this level, you may have loaded a program at this level if you've ever had to like flash your BIOS. Okay, so we can imagine going through this process for our other instructions. So it's in addition to load, we can talk about load immediate or load indirect, and they're similar enough that we should be able to sort of look at that table that we made and write those ones and zeros. So the load immediate, I get lazy and stop writing all the zeros, which is, it's mostly zeros, but in the load immediate, the once I have the instruction, once I'm ready to execute, the operand then came along with the instruction that is the data I want in the accumulator. So I would just say take it out of the instruction register enable, and put it straight into the accumulator. And then I would have a load immediate, a different addressing mode. Load indirect, it was sort of an address of an address. So the execution cycle, and so what I get from the instruction register, that piece of data is an address. So I'm taking it in that sort of fourth row there, the one with just two ones. I'm taking it instruction register enabled, taking that value out of the instruction register and it's an address, so putting it into the memory address register. Now in step 5 there, I'm ready to read something, and what I'm reading is another address, and addresses go into the memory address register. So my memory read is active. My memory data register enable is active, so I'm putting the value on the bus, and then it's being fed into the memory address register because I had in loaded indirect, I have an address of an address. And then in my last step, I'm finally pointing my memory address register. The second address is pointing to the actual data I want now. So once again, I'm going to read it. That puts it into the memory data register. I want to move it around. So the memory data register is going to put it on, is going to enable, is going to put it on the bus. And then I take it into the accumulator. So we see here sort of explicitly with these ones and zeros that it's mostly zeros. So most of the pieces, most of our hardware, most of our components of our computer are sort of inactive. So as we get down to this control sequencing to do what we want it to do, and we don't want any interference, so we get there's a lot of inaction. So our normal concept of the computer, input, output, memory, and CPU, which is the ALU and control combined, got named the von Neumann architecture. If you add in the stored program concept, which we've been doing because we are imagining our memory has both instructions and data in it. And so when we combine the stored program concept and our normal pieces of the computer, we talk about the von Neumann architecture. And so then if he's going to take credit for the architecture, he's also got to take credit for the problems with the architecture, which are the bottleneck, that we're going sort of back and forth to memory, and that can be that back and forth and one thing at a time process slows things down and is the main sort of bottleneck of computing. And then we will try to speed things up. We'll try to cache. We'll try to pipeline. We will try to do things in parallel when we can. So we're going to do what we can to overcome this bottleneck. Okay, and that's just another reference to the von Neumann bottleneck. So that's where I'll end this video, and we will continue this in the next video. Thanks for your attention.